Bismillahirrahmanirrahim. Dear viewers, Assalamu alaikum. As you know that we are in the process of learning various synthetic applications of different alcoholic protectives. And in the previous few videos, we had studied acetyl, benzyl and trityl protection as well as uh, the applications or formations of silyl ether for the protection of alcoholic functionalities. Today, we will add a few more examples in the given subject. So, let's proceed towards example. In this example, we are going to modify a bifunctional molecule shown here towards the final product, which requires nucleophilic replacement of bromide with the methyl acetylide ion. So, uh, the structural analysis suggests that by treating the starting material with methyl acetylide, we would be able to get our desired product. So let's come and solve this. In the first step, we have uh, protected our hydroxyl group in order to stop this hydroxyl group to take part in the chemical reaction. Why is there need to protect this hydroxyl group? We will discuss it in the later part of the video. Let's proceed towards protection. We have chosen a silyl group for the protection of this hydroxyl functionality. Once it is protected, now there is no more side reaction possible for the formation of our desired product. Hydroxyl group is now converted or transformed into corresponding silyl ether. The obtained molecule is now treated with sodium acetylide, and we are getting here corresponding incorporation of acetylide moiety in our molecule with the removal of Br negative. As you know that now in the final step we are required to incorporate methyl group as well by replacing this hydrogen atom of terminal alkyne, and that would be possible by considering the acidic properties of terminal alkynes. As we know that terminal alkynes are acidic in nature because the carbon atom of terminal carbon atom is sp hybridized, having greater ability to attract shared pair of electrons towards itself, meaning the terminal carbon atom in this case is slightly electron rich and the hydrogen atom is electron deficient. So this hydrogen atom of terminal alkyne is acidic in nature, which could be picked up a base. Sodium sodamide here acts as a base. It picks up the proton, creating negative charge on the terminal carbon atom. Now this negatively charged terminal carbon atom is a nucleophile. It could act as a nucleophile and attack on the methyl iodide, which is substrate here, and corresponding methylation takes place. The final step is now the deprotection of TBDMS, and we are very well aware how to achieve the deprotection in that case. Yes, by using fluoride ions. And TBAF, tetrabutyl ammonium fluoride, is a good source of fluoride ions. So our TBDMS group is deprotected and our original hydroxyl functionality is now generated. So this is the formation of our desired product. In addition to this route, we may think to follow some other routes as well. So let's, I am going to share here the ChemDraw file to see what other routes we could think and whether they could be applied or not. Yes, here we are. This is the ChemDraw file here showing our route for the synthesis of our desired product. So this is the successful route here, which enabled us to get the final product synthesized. So the first option we will think here, we will consider that why not to choose sodium acetylide directly without any protection, without any protection. Let's see what will happen. This is acetyl and all of us know that the negatively charged ions, they are capable to act as nucleophiles as well as they are capable to pick up proton and act as a base. So if we are designing to use directly sodium acetylide here, our original molecule here is having two electron deficient sites. One site is of electron deficient hydrogen atom and the other is electron deficient carbon atom. What will happen? This negative charge ion will go on either to attack on the proton or to attack on the electron deficient carbon atom. There are two options here, but we know that acid-base reactions are preferably done as compared to the nucleophilic substitution reactions. Why? Because acid-base reactions uh, are more feasible, they require less energies to proceed as compared to the nucleophilic substitution reactions. So the preferable reaction would be the creation, the pickup of the proton and formation of corresponding negatively charged species, as we are going to draw here. So we will get this negatively charged ion. Now this negatively charged ion will go to attack on this carbon atom, on the carbon atom of alkyl halide. That is also electron deficient here. With the removal of this Br negative ion, so rather to move towards our desired product, we are moving towards a 1, 2, 3, 4, 5, 5-membered cyclic ring that is containing one oxygen atom, and on carbon number 1, 2, 3, there is substitution of alkyl group. On the second carbon, there is alkyl group substituted. So what is this? This is a derivative of tetrahydrofuran. तो क्या हम ये tetrahydrofuran चाहते थे? Definitely we were not looking for formation of tetrahydrofuran. Our aim was to synthesize this molecule. And with the formation of this molecule, this tetrahydrofuran, we cannot move further for our desired product synthesis. So one thing is now clear in our mind that we must have to protect this hydroxyl group to move further for our desired synthesis. Okay, so this part of the molecule is this part of the reaction could be deleted now, as we know that now it is not going to work here. Now there are number of modifications you could easily do. For example, if the desired product is uh, not this methyl group, rather it is a benzyl group here, then how will we proceed? Obviously, quite simple. We will protect this hydroxyl group. As you know that, you now clearly know that the protection of this hydroxyl group is necessary. Once it is protected, now we are going to use sodium acetylide as a nucleophile, and we get this product here. Now, when we have achieved the formation of this product, we just require benzylation on the terminal alkyne. Obviously, that would be done by using the similar route. We are using sodamide here as a base and alkyl halide, benzyl halide as a substrate. So this could be benzyl chloride or benzyl bromide. With the removal of this bromide, we would be getting the benzylation of the terminal carbon atom, and in the final step we have deprotected our protecting group, that is TBDMS group, to get uh, regenerated our original hydroxyl functionality. So let's move towards next example. It is example 5. We do not want here the benzyl group. Rather, we want here ethyl group. Let's go. This is our desired modification which we are designing here. I think now you should clearly well aware how to proceed towards the formation of our desired final molecule. Let's see. Let's move towards forward. Starting from our starting material, we have moved towards its protection. Then incorporation of this terminal acetylene molecule, terminal acetylide group here. Once it is incorporated, now we want the replacement of this hydrogen with ethyl. Since this terminal hydrogen is acidic in nature, sodamide would definitely help us creating a negative charge on this terminal carbon atom by uh, one picking this proton. Now the ethyl bromide, ethyl iodide could be used as a substrate, resulting in the formation of substituted ethyl group substitution. Once we have moved over this step, we know that now we are going to protect this TBDMS group, and that deprotection could be carried out by using what? Yes, tetrabutyl ammonium fluoride. This TBDMS group is now gone here, and our original hydroxyl functionality is generated. So, is it clear to all of you? Let's move towards another example. This is example 6. These are 1, 2, 3, 4 carbon atoms. 1, 2, 3, 4. Now, if we are requiring that this bromine should be replaced, let's suppose with aniline. This is NH group. This is aniline. Okay. Yes, we know that before proceeding towards our desired product formation, we must have to protect this hydroxyl group, and we have done the same. We have protected this hydroxyl group with PBDMS group. Now we know that we want that aniline moiety should be incorporated in this molecule. That could be done by the nucleophilic attack of aniline here with the replacement or with the removal of bromidine. We know that aniline bears a lone pair of electrons from the nitrogen atom. That is now attacking on the electron deficient carbon atom. But electron deficient carbon atom. This is basically the electron deficient carbon atom here. I'm showing you. Yes. So with the removal of bromide, we are getting our desired fragment of molecule being incorporated. Yes, Br negative has now left, and now here it is the substitution with aniline. Let let's count number of carbon atom are the same or not. 1, 2, 3, 4. 1, 2, 3, 4. Yes, it is fine. Now in the final step, what we are required? We require just to detach or deprotect this PBDMS group, and that could be done by using, yes, tetrabutyl ammonium fluoride. So this DMS group is born here by using tetrabutyl ammonium fluoride, resulting in the regeneration of our original hydroxyl functionality. So we are successful in getting our desired modification. Another interesting route or interesting uh, example I am going to share. Let this is example now 7. We are well aware here. Please focus on this uh, molecule. This molecule is now capable to undergo almost all the reactions that alkyl halide do. Alkyl halide reacts with amines. Alkyl halides uh, they react with metals to form corresponding uh, organometallic compounds. They react with they react to form Grignard reagent. And Grignard reagent itself has a number of synthetic applications. So let's move towards the formation of Grignard reagent. Yes. Before moving towards formation of Grignard reagent, let's delete all the previous examples so that they will not disturb us while proceeding towards further examples as well. Now, first of all, let's think what Grignard reagent do. Grignard reagent reacts with electron deficient molecules uh, to undergo corresponding transformations. Here I am writing down the structure of Grignard reagent. As you could see here, the carbon atom in the Grignard reagent, it is electron rich. So this electron rich carbon atom, this electron rich alkyl group have totally different characteristics as compared to electron deficiency or deficient alkyl halide. So Grignard reagents have totally different behavior towards chemical reactions as compared to the alkyl halides. For example, we could replace this bromine by R group by using Grignard reagent. So how would we be able towards this transformation? Let's move further. We are going to utilize magnesium metal in the presence of dry ether. So these are quite suitable conditions for the formation of Grignard reagents. Here, in this case, this is not now Br, it is MgBr. It is MgBr. So magnesium is inserted in carbon bromine bond. So we have got the formation of a Grignard reagent here. The carbon atom of the Grignard reagent is electron rich in nature. Yes, here this carbon atom is electron rich. Now it could undergo a number of modifications. The first one we are requiring here in example 7 is by incorporation of R group. So it could be easily done by treating this Grignard reagent with alkyl halide or maybe methyl, ethyl, benzyl, etc. Now this negatively charged portion of the molecule here, which is electron rich, it is going to attack on this carbon atom with the removal of corresponding halide. So once this halide is removed, we have got our desired transformation here. It is now OR. Now R group is substituted in this molecule. Yes. So it is the formation of our desired product. Is not it? तो क्या ये आसान है? हाँ, अगर बेसिक कॉन्सेप्ट हम फॉलो करें तो ये बहुत आसान है. ये ट्रांसफॉर्मेशंस का तो मुश्किल है. अगर इन एग्जांपल्स को करते हुए आपने एक बार भी ये सोच लिया कि ये मॉडिफिकेशंस मुश्किल हैं, तो मेरा ख्याल है कि आप अपने डिज़ायर टारगेट तक नहीं पहुंच पाएंगे. ये जितनी एग्जांपल्स मैंने यहाँ पे आपको शो की हैं, जस्ट सिंपल मॉडिफिकेशंस, जैसे एग्जाम्पल 3 में देयर वाज अ मिथाइल ग्रुप, एग्जाम्पल 4 में क्या था, वही रूट था बट विद इथाइल ग्रुप, एग्जाम्पल 5 रूट सेम but substitution with benzyl group. In example 6, we have considered now the utilization of aniline as a nucleophile. And here it is example 7. We are following the formation of Grignard reagent, and now all those reactions that Grignard reagent undergoes that are being carried out here. For example, you know that Grignard reagent reacts with water, is not it? Yes, it reacts with water, and the uh, alkyl group, electron rich alkyl group here in the Grignard reagent, it picks up that proton, yes, resulting in the formation of corresponding molecule. So it was CH2 group here, uh, yes, this one group CH2, which is now converted into corresponding CH3. Just electron rich CH2 moiety has picked up a proton from water and is now converted into corresponding methyl group. That is quite easy. So just focus on your mind and think what kind of other reactions Grignard reagent undergoes. You may remind that Grignard reagents react with aldehydes and ketones as well. So this is acetaldehyde. What will happen here? The electron rich end of the Grignard reagent, this one, it would attack on the electron deficient carbon atom of the aldehyde group. It could be drawn here. This is the acetaldehyde. I am going to shift here. So this is the carbon atom which is electron deficient, and the carbon atom of Grignard reagent is electron rich, that is acting as a nucleophile and is attacking on the carbonyl carbon atom. This pi bond is broken down. So here an interesting formation. Yes. So this was the carbon atom which was attacking on the carbonyl group. This is carbonyl group. Carbon oxygen bond has broken down, uh, resulting in the formation of corresponding co-negative. During aqueous workup, we are able to get corresponding OH group here. Yes. And in the final step, you would be going towards the deprotection of these DMS group, and we are well aware that these TB DMS group are deprotected in the presence of tetrabutyl ammonium fluoride. So we are successful here in getting our desired modification. The same type of deprotection that could be done in this case. The various other modifications which we want to carry out from this Grignard reagents, they could be done by following the same rules, corresponding rules as well. Here it also requires deprotection, and that is done under the same conditions. I hope, dear viewers, that you could have followed all these examples, and now it is clear to you that when to protect the hydroxyl group and when not to protect this hydroxyl group. So in all these examples, we were required to carry out first protection of hydroxyl group and then proceed towards our desired modifications. We will meet in the next video. Thank you very much, and Allah.